All right, this is topic 6, heat exchangers and condensers. We're going to learn the physical characteristics of the heat exchangers and the condensers and the different parts of them and such. But it's kind of sneaky. We also have to learn some heat transfer in this as well. So we'll be introducing some equations, and not necessarily is it usually in the learning material. You kind of have to go to heat transfer and thermodynamics chapters to kind of get the whole picture. But we've included some heat transfer rate equations in this learning document here. So we'll get to it, and it won't seem so bad. So I'm sitting here in the learning material, and you'll see we're going to start right here in the introduction. And it just says, purpose of a heat exchanger. And I think we all know that it allows the transfer of heat from one fluid to another, and it always flows from hot to cold. And the amount of energy or the amount of heat, well, that's where these heat transfer equations are going to come in. And I'm going to introduce them right now, just quickly, so we can just get used to them. First equation we're going to look at is Q dot. First of all, we have to know what that is in terms of the unit. That unit is BTUs per hour, and that's what the dot means, per unit time. So this is BTUs per hour. I can always convert BTUs per hour to megawatts with this conversion. There are 3.41 times 10 to the 6th BTUs per hour in 1 megawatt. That's on your NRC equation sheet, so don't forget that. So the first equation to solve for the heat transfer rate, BTUs per hour, is mass flow rate, which is in pounds mass per hour, times change in enthalpy. Enthalpy is a unit of heat, essentially, and we're going to be talking about the amount of heat in 1 pound mass. So this is actually specific enthalpy, and we learn about this more in heat transfer than we really do in components. But we have to introduce it now if you're doing components first. And the unit for enthalpy, specific enthalpy, excuse me, is BTUs, the energy contained in 1 pound mass. And if you look at the units, we get BTUs per hour whenever we multiply mass flow rate times change in enthalpy, right? So if we have a greater mass flow rate, we can have a greater heat transfer. We can send a lot more of the hot energy to the cooler fluid. Or if we have a greater change in enthalpy. And we can use this equation anytime as long as we can find these unknowns. All right, next one. Next equation has limitations on it. Q dot, once again, in BTUs per hour, which we know we could convert to megawatts, is equal to, once again, how much the rate at which we're putting water to, or oil, or whatever, the rate at which we're sending the fluid to the heat exchanger, times this. It's called a specific heat capacity. So mass flow rate is pounds mass per hour. Specific heat capacity is essentially the ability of the fluid to hold energy. And its units are BTU, and it's specific, so it's going to be per pound mass degree Fahrenheit. So the unit for specific heat capacity, which is called C sub P, is BTUs per pound mass degree Fahrenheit. And then we're going to look at the delta T, T hot minus T cold. The hot temperature minus the cold temperature, which is a differential temperature in the heat exchanger, right? And that's going to be in degrees Fahrenheit. And let's look at our units. The degrees Fahrenheit cancel out, the pounds mass cancel out, and once again, we have BTUs per hour. Now, there is a limitation here. In the heat exchanger, if there is a phase change, meaning water is turning to steam or steam is condensing to water, and there is a change in the atomic spacing, then that's not allowed. I can't use this equation. There can be no phase change when using this equation. No phase change allowed. That's going to be key. That just happens to be a limitation in this equation. So the first one you'll remember was the heat transfer rate was equal to mass flow rate times change in enthalpy. This one will be C sub P times T hot minus T cold. Now the last equation that we have. Once again, if I want to know how much heat is being transferred per unit time, heat transfer in BTUs per hour is equal to U, which is the overall heat transfer coefficient, times A, which is area, times the difference in temperature. Such that if I had a lot of area, I can transfer a lot of heat. If I have a really good overall heat transfer coefficient, I can transfer a lot of heat. If I have a large differential temperature, I can transfer a lot of heat. This can be used anytime if given enough information. What's most commonly messed up is this differential temperature. This differential temperature is the average temperature of the hot fluid minus the average temperature of the cold fluid. That's going to be key in using this equation. And once again, we can figure out what the unit for heat transfer coefficient is, because this is Fahrenheit and this is going to be square feet, and we need to get BTUs per hour. So you can kind of figure out that, oh, well, U is going to be BTUs per hour square foot Fahrenheit. And then that would cancel out the Fahrenheit, cancel out the square feet, and you'd be back to BTUs per hour. But we talk about this a lot in thermodynamics. So just 3 equations that we're going to get familiar with and start learning how to use. All right? Under here it starts, section 2.0 refers to the types of heat exchangers. And the most common types we're going to use are shell and tube type heat exchangers, which are right here. And they have some advantages. And we'll see what those are. But first of all, the most basic and common type of this is a shell and tube heat exchanger. And there's 2 fluids here. There is one fluid that is flowing through the tubes and one fluid that is flowing through the shell. And so that they're not in contact with one another, that they're not mixing, but there's a heat transfer surface area of the tubes. So generally, the higher pressure fluid will go inside the tubes and the lower pressure fluid would be in the shell. All right. Now, the fluid that's coming in the shell side, you can see coming here, it's going to come in. Hopefully, it would mix really good along the tubes, and then it goes out. But it's going to tend to take this path of least resistance, right? And we want to know the basic components of a heat exchanger. And we have tubes, and then we have the shell. And the last thing we have is we have this thing called a tube sheet. And if we were to look at it, here is a tube sheet, and I haven't even shown the shell yet, and it's got all the tubes in it. These are the tubes, and then the water is going to come in, and if I was to look at the end of this, it would have holes where the tubes are on each end. So water can go through the tubes, and this on this end, it too has the same exact holes. So water could flow, or whatever fluid it is, could flow through the tubes. Then on the other side of this, we would have the shell. And so fluid would come in here and hopefully would go on the other side of the tubes and mix around really good and then leave. So I would transfer energy from the hot fluid to the cold fluid. The key is I really want to keep them in contact with one another via these tubes and shell. If I don't, and if I just short cycle real quick, I'm not going to get good heat transfer. So we need to do something to promote contact time within the shell of that heat exchanger. So let's turn the page. And we do that. We actually, if you'll look, let this focus for a minute. There we go. We put these things called baffles in there. Yeah, the baffles, they're arranged to cause the fluid to cause all kinds of directional changes so that you get a combination of cross flow and counter flow and lots of good contact from the shell side fluid to the tube side fluid. All right, next thing we talk about is the tubes in here. We have a couple variations of tubes. the tubes could be straight. They could just go straight through. And this is a good example. You can see the end of the tube sheet here where there's the penetration and the fluid can go all the way through. Good advantage right here of straight tubes is they're easily cleaned. We could put little balls in there, like sometimes a lot of plants have what's known as an Ammer tap system. I could put little balls in there and they would go straight on through, and they could mechanically clean the inside of the tubes and remove any debris or buildup that's occurring. Another one I have, no, it's straight in nature, but it's bowed. This is pretty cool. Bowed tubes, they're going to tend to expand when they get hot and then contract and they start to bow. And that has the advantage of, right here you'll see, is it'll crack off any hard scale buildup that tends to build up on the outside of the tubes. So you'll see a lot of these in the plant. Probably predominantly your heat exchangers will be straight tube if you go look at feed water heaters and turbine building closed cooling water or reactor building closed cooling water or whatever. Good portion of your heaters, heat exchangers rather, are going to be straight tube heat exchangers. The last two that we look at here, we could have a U-tube heat exchanger. U-tube, water or flow comes in, it goes around and comes out, and there's only one tube sheet. That's an advantage. Yeah, real cool. Disadvantage though, these are a little bit harder to mechanically clean because you got to take this turn in the heat exchanger. So, in the boiling water world, we don't see a lot of these. In the pressurized water world, they have a lot more. And finally is a coil tube heat exchanger, and you can see this. Now this is typical of what you might see in a sample sink. It says expansion is absorbed with this floating head arrangement, so if it was heating up and cooling down, and they are suitable for high pressure environments, but they're usually small and are often used at sample sinks, and that says they're often used as sample coolers. So just basic construction of the tubes and basic construction of the heat exchangers itself. The next one, next time we come back, we're going to be looking at the flow through the heat exchangers and looking at some temperature profiles, which will be real important.